Hello viewers, welcome back to this channel. So in this video we are going to be handling the second video under electrochemistry. So this video is presented to you by Yusuf. You advise subscribe to the channel and share the video to your friends so that you can all benefit as a group. Now proceeding with our topic, in the first video we are handling electrochemistry, where we talked about electrolysis together with the calculations that can be examined or that can be said about electrolysis. So electrolysis is not mainly said in U.A.C.E, but we mainly said these other parts of electrochemistry, and the other parts of electrochemistry are going to require you to be intensely focused and intensely serious about your practice so that you can master all the calculations together with the definitions. Now, the advantage about electrochemistry is that most of the definitions of the different standard definitions are going to be derived from the formulas. So in this video, we are going to be talking about conductivity of solutions together with the factors that are going to be affecting the conductivity of these solutions, which we called earlier on electrolytes. And we defined electrolytes in our first video as solutions as components that can be in their molten or solution state but are able to conduct electricity, and that's what we call electrolytes. So we're going to start by saying that when electric current flows through an electrolyte, there's going to be a resistance to the flow of this current, and the current that is going to be flowing through a given solution under given conditions is going to be inversely proportional to the reciprocal of resistance. In other words, we can present that by a formula by simply saying that current flowing through an electrolyte or an electrolytic solution is going to be the reciprocal of the resistance of that electrolytic solution. And you're going to be looking at this more in details. This was just an introduction, so you're going to be looking at it under a definite interval of conductance. So we're going to be looking at the common terms that are going to be used in the calculations that are going to involve conductivity of different electrolytic solutions. So starting with conductance, we are going to define conductance as the reciprocal of resistance of an electrolytic solution. So conductance is simply, even when you're calculating it, it's going to be, if you're asked for conductancy or you're asked to calculate for conductancy, it's going to be simply the reciprocal of your resistance, and resistance most of the times is going to be defined, or sometimes you're going to be given resistance and you're required to find conductance. So what you should take away here is that conductance is simply the reciprocal of resistance, and you're going to give it the SI units to be Siemens, and Siemens is denoted by capital S. And now Siemens also has another alternative or another meaning or other units from which you can write Siemens. So Siemens, someone can write it as per ohm. Now we're going to say that high resistance means low conductance, and also low resistance means high conductance. If at all in any given electric solution we are having or we are experiencing low resistance to the flow of current, that means that conductancy of that electrolytic solution is going to be high. And if you are having high resistance to the electrolytic flow of current within that solution, that means that the conductance of electricity or electric current within that given electric solution is going to be low. Now, from that, let's look at resistivity, which is going to be denoted by a constant which is going to be known as a constant of resistivity. So we write it as is similar, it's quite similar to exponential constant, but for it it's not E, it's just P, which is inverted. So P, but in terms of an italic format. So you're going to say that to compare resistance of different electrolytic solutions, the idea of resistivity is going to be used. And with this, we are going to define resistivity as simply the resistance of a given solution which has been placed between two parallel electrodes, of cross-section area 1 meter squared and are going to be separated by a unit distance. And by saying a unit distance, we mean a distance of 1 meter apart. So in some books or in some of the notes that may be available by your teachers, the conclusion may vary. So it's going to be resistance of a solution placed between two parallel electrodes with a cross-section area of 1 meter squared, but the part about distance, some books say with a unit distance apart, because unit distance apart is the same as saying being separated by a distance of 1 meter apart of the two parallel electrodes. Now the key point here is that you must define that it's going to be the resistance of any given electrolytic solution, but this electrolytic solution must be between two parallel electrodes. And these parallel electrodes must be of cross-section area of 1 meter squared, and they must be separated by a unit distance, or they must be separated by a distance of 1 meters apart. So proceeding, we are going to say that resistance, which is going to be denoted by capital R, of any given electrolytic solution is going to be directly proportional to the length between the parallel electrodes, because we say that they are going to be separated by a unit distance. So that means that resistance, which is denoted by capital R, is going to be directly proportional to the length that is separating the two parallel electrodes, and we are going to name this as our equation 1. Now we're also going to say that the resistance R of any given electrolytic solution is also inversely proportional to the cross-section area of these parallel electrodes from which our electrolytic solution is placed. So joining these two, so we are going to, this was our first equation. The other equation is going to be representing this statement, that resistance is going to be inversely proportional, which means that 1 over the cross-section area. Now cross-section area is going to be denoted by capital A. So we have resistance from equation 1 to be directly proportional to length, and in equation 2 resistance is inversely proportional. In equation 1 it was directly proportional to length. In equation 2 resistance is inversely proportional to the cross-section area. So we are going to combine these two equations and we bring them together. So 1 is going to be the upper statement whereby resistance is directly proportional to length, and combining the other second equation, we are going to have it that resistance is also inversely proportional to the cross-section area. Now removing the proportionality constant or the proportionality sign, we need to bring in the proportionality constant. And the proportionality constant we are going to bring in here is going to be the constant of resistivity. So it means that for us to eliminate this sign of the proportionality, we are going to introduce the equal sign. But the moment we introduce the equal sign, we introduce a constant of resistivity and we maintain our length divided by area. And here we are going to be defining each and every letter as we already defined them. And you're going to say that R is going to be the resistance, this symbol P, pi, which is going to be the constant of resistivity, and L is going to be the length that is present between the two parallel electrodes as we place it in the definition of resistivity. And then A is going to be the cross-section area of our electrodes. So from our equation 3, which we have already combined, we are going to make our constant of resistivity the subject. So if you make constant of resistivity the subject, you're going to multiply A here, and then you divide by L. And you're going to end up with the subject of resistivity to be equal to area multiplied by resistance divided by the length between the two parallel electrodes. Now you're going to say that resistance is going to be measured in ohms, and the sign for ohms is written like this. And the area is going to be measured in meters squared. Length is going to be measured in meters because those are the standard units. Now the reciprocal of resistivity is going to be measured in terms of ohms per meters. But remember that ohm per centimeters can also be used depending on the SI units that you are being given in the different questions. If at all your question is in terms of ohm centimeters, you use that. If it is in terms of ohm meters, you also use that. So proceeding to the next term, we are going to look at electrolytic conductivity. Now this one is a very commonly examined term. Now you're going to define, you can either define it in terms of its formula, or you can define it in terms of its definition. I say that the advantage about this topic is that you can give definitions in terms of formulas, but you can also give definitions in terms of their standard definitions. So looking at electrolytic conductivity, we are going to also call it specific conductivity or specific conductancy. So anywhere you see specific conductivity or specific conductancy, they are referring to electrolytic conductivity. And they are going to say that electrolytic conductivity is going to be defined as the conductivity of any solution, of any given solution of an electrolyte which has been placed between two parallel electrodes of cross-section area 1 meter squared separated by a unit distance, or separated by a distance of 1 meter apart. I told you unit distance is the same as a distance of 1 meter apart. So here, this definition is varying from the definition of resistivity in that by the starting term. The other one, you define it as the resistance of a solution. Now, when you're defining electrolytic conductivity, what's going to vary only is going to be the starting term, and the other terms are going to remain constant. So it's going to be the conductivity. Instead of the resistance of a solution is going to be the conductancy or the conductivity of a solution. And the other terms are going to remain the same as we define them under the definition of resistivity. So simply it's going to be the conductivity of a solution of an electrolyte that has been placed between two parallel electrodes. Now notice that these electrodes must be parallel. I didn't give a sketch for that, but if you go into those textbooks exams, then you'll see that those electrodes must be parallel. So they must be placed between two parallel electrodes of cross-section area 1 meter squared, and they must be separated by a distance of 1 meters apart. Now, or you can give the definition of electrolytic conductivity in terms of its formula. And by formula, electronic conductivity, which is denoted by capital K, is the same as the reciprocal of resistivity. So when you're defining electronic conductivity, you can also define it in terms of that, simply by saying electronic conductivity is going to be the reciprocal of resistivity. Now this one was not O, it's of, reciprocal of resistivity. Now what you're going to add on here, you're going to add on of an electrolytic solution, because this resistivity must be of an electrolytic solution. So the reciprocal resistivity of an electrolytic solution. And by formula we shall come and say that K is equal to 1 divided by the resistivity, which, or someone can call it constant of resistivity. But remember, we gave the formula for resistivity where we made it the subject, and it said that resistivity is the same as area multiplied by resistance divided by length. So if you find reciprocal, you're going to end up with length divided by the product between the area together with the resistance of the solution. And when you separate the two, you're going to have reciprocal resistance multiplied by length divided by area. And I hope you remember reciprocal resistance, what it means. And then length divided by area, we are also going to talk about it to be a specific term. And we shall see the final formula we can use to calculate for electrolytic conductivity. However, all these formulas that have been derived here, they are going to be very useful when you come to calculations. So I'm going to say that the SI unit for electrolytic conductivity is going to be Siemens per meters, which can be denoted as capital A's per meter. And you're going to say that Siemens per meter or per centimeter can also be used depending on the SI units that you have been given in the respective questions that they're going to be examining you with. So 1 Siemens per meter, we say that Siemens is the same as per ohm. So 1 Siemens per meter is the same as 1 per ohm per meter, and 1 Siemens per centimeter is the same as 1 per ohm per centimeters. Siemens is the same as per ohm. So that's how the conversions can be made. Now proceeding, we are going to be looking at another term which is going to be known as the cell constant. Now from the cell constant, we can say that from the formula of resistance to be equal to reciprocal resistivity multiplied by length divided by area, the cell constant is going to be the value of length or the ratio of length to area, and its unit is going to be per meter, because remember that length is measured in meters and area is going to be measured in meters squared. So if you divide the two, you're going to remain with meters power -1. So that's why the unit is going to be per meter. Or in terms of centimeters, it's going to be per centimeter. Now you're going to say that L and A, length and area for any cell, are going to be constant. So we can define cell constant. In case you're examined by that, we can define it as the distance between two parallel electrodes of a cell being divided by the cross-section area of simply one electrode. So for us to get cell constant, we need to get the distance, which is the length between the two parallel electrodes, divided by the cross-section area. But this cross-section area must be of one electrode, not the two. Remember that there are two electrodes. So the distance must be between the two electrodes, but the area that you use, it must be of one electrode, not two. So you can come and conclude and say that, therefore, resistance is going to be equal to resistivity times length divided by area, which you already looked at in the introduction. But you have said that the length divided by area is the same as cell constant. So that means that resistance can be given by resistivity multiplied by cell constant. Now, these are very vital elements. Before you go to calculations, you need to understand how to derive all these formulas. Because when you go to calculations, it will be very easier for you to understand each and every step I'll be making. If at all you understood how these derivations of these formulas come about. Now remember, when you're deriving the formula for electric conductivity, we stopped on 1 divided by R, which is the reciprocal resistance, multiplied by length divided by area. Now we have said that length divided by area is the same as cell constant. But also when you're defining conductancy, we simply say that this is a reciprocal resistance. So since this is 1 over R, which is the same as reciprocal resistance, it can be termed as conductance. Because we said conductancy under its definition that is the reciprocal of resistance. So you can simply say that electric conductivity can also be given as conductancy of any given solution multiplied by the cell constant. Or we can say K is equal to length divided by area divided by resistance. Or resistance, because the R is for resistance, whereby this is going to become cell constant divided by resistance. Now let's proceed and say that molar conductivity, now the next term is going to be molar conductivity. Now molar conductivity together with electrolytic conductivity are some of the mainly asked terms under electrochemistry. You need to know the standard definition, and if at all you happen to forget the standard definition, I repeat this, if at all you happen to forget the standard definition, then you can refer to the definition by formula. But most of the times, opt for the definition which is standard, because sometimes we can't award all the marks by simply mentioning a simple definition like this. So we shall be giving half a mark for a student who has decided to define by a formula, in case we allocate many marks. But if you allocate like half a mark, you are free to define the given term by its formula. So let's look at molar conductivity as in its definition. Just like you are hearing molar, that means that whatever you're talking about must be of 1 mole. Just like any other terms that you have been defining under the different topics of chemistry as uploaded on this channel. So we're going to say that molar conductivity is going to be that conductivity of a solution, but this solution must contain 1 mole of any given electrolyte which has been placed between the two parallel electrodes of cross-section area 1 meter squared and being separated by a unit distance, or simply a distance of 1 meter apart. Now here what varies is that, like you can see the standard definitions, they're all having in common this statement, that the electrolytic solution must be placed between two parallel electrodes which are of unit cross-section area, or you can say cross-section area 1 meter squared, and separated by a unit distance, or you can say separated by a distance of 1 meter apart. So what's the standard definitions, the good thing is that they are common. That means that they can easily be remembered. So what you need to do is simply to dedicate a time and summarize all of them so that you can discuss them and later you can master the respective definitions to the respective questions. So molar conductivity is going to be that conductivity of an electrolytic solution, but that electrolytic solution must be containing 1 mole of an electrolyte. But that solution must be placed between two parallel electrodes of unit cross-section area, or cross-section area of 1 meter squared, and separated by a distance of 1 meter apart, or separated by a unit distance. They are all correct terms. Or we can define molar conductivity in terms of its formula by simply saying that it's going to be the electrolytic conductivity divided by concentration. Like I said, that supplement this by concentration of an electrolytic solution. So supplement this definition by concentration of an electrolytic solution. So it's the electrolytic conductivity divided by concentration of an electrolytic solution. So by formula it's going to be as follows. So molar conductivity, which is denoted by inverted V with a subscript of C, is going to be equal to capital K, which denotes electrolytic conductivity, divided by concentration. Concentration is denoted by small c. Now we are going to say that since the reciprocal of concentration is the same as dilution, I hope you are told that reciprocal of concentration is going to be dilution, then molar conductivity is going to be the same as K times 1 over C, but 1 over C is the same as dilution, and we denote dilution by V. However, this is not going to be commonly used in the calculations. So molar conductivity can also be equal to electrolytic conductivity multiplied by dilution, since dilution is the same as the reciprocal of concentration. So proceeding, we are going to say that the SI unit of the molar conductivity is going to be meter squared per mole, but also Siemens per centimeter squared per mole can also be used. So the conversions of the SI units can also be equal to that. Now here is the most important factor. So here we are going to say that the formula of molar conductivity to be used in the calculations is going to depend on the units of the electrolytic conductivity given. And you should underline this if possible. If you are taking notes, make sure that you underline this part, because this is where all the calculations that you're going to be making are going to be messing up from. Also, remember that also this application is going to be covered under ionic chemistry. So ionic chemistry and electrochemistry, there is a point at which they are linked, whereby you have to calculate for molar conductivity using the electrolytic conductivity value given. So for us to find the formula of the molar conductivity we are using, we are going to depend on the SI units of our electrolytic conductivity, which has been given in the question. So in case it's present in any of these SI units, we are going to be using two different formulas. And you're going to say that the formula, first of all, what you should note is that the formula that is going to be used is going to depend on the SI units of the electrolytic conductivity as provided in the question. And secondly, now electrolytic conductivity can also be the same as Corash's law of independent assortment. Like we are going to look at Corash being also providing to us SI units of electrolytic conductivity. So we shall be considering those two for us to identify a suitable method of molar conductivity. The stable method you can be using to calculate for molar conductivity. So here we are going to provide two conditions, and you're going to say that if the units of the electrolytic conductivity that are being given are in terms of Siemens centimeter squared per mole, or remember that Siemens is the same as per ohm, so per ohm per centimeter squared per mole, for as long as you see centimeters. For as long as you see centimeters, that's why it's the only thing I brought here. So for as long as you see centimeters, the formula for molar conductivity is going to be the same as 1000 K divided by concentration. This is only when you see centimeters under the SI units of electric conductivity, or after using Corash's law. Now, the other condition, or condition 2, is going to be the same as when you're given U.S.E units of electrical conductivity to be in terms of meters squared, or to be in terms of meters instead of centimeters. So if they're in terms of meters, the formula is going to change, and molar conductivity is going to be equal to electrical conductivity divided by concentration, but this concentration is going to be multiplied by 1,000. So you can conclude by saying that the expression molar conductivity is equal to K over C is only going to be used if the units are going to be inconsistent. So if at all, but this is a very rare case, usually the question is going to specify we are either going to use SI units in terms of meters or centimeters. So you have said that if it's in terms of centimeters, it's 1,000 K divided by C. But if it's in terms of meters, it's going to be K divided by 1,000 C. Those are the only two conditions, and you need to understand them properly before even you proceed to any other part of this video. So this one is going to be a very rare case, and you're going to we are almost not going to consider it, because most of the times we give consistent units. So we are going to make a note that when the definitions are going to be stated in terms of formulae, each term in the formula should be well defined, and I've already talked about that. So now with what you have covered, we are going to start applying the formulas and the different definitions or the different terms that we have been talking about. So first of all, I've provided 2 questions. Now these questions, some are going to be definitions. So for the definitions, you can code down the questions and you discuss them with your friends. What you're going to be focusing at mainly are going to be the calculations. So first is going to be calculations that are going to be involving electrolytic conductance, and the examples that you're going to be having, they are going to be well explained and well detailed and written out correctly upon what you have discussed earlier on. So in this question, we started by questioning about the definition of cell constant, and part B is going to question us Roman number 1 to calculate for the cell constant. I hope you remember what cell constant is. Cell constant is the length between 2 electrodes divided by the cross-section area of 1 electrode. But you can't get cell constant without other confluences. So you have to first read the question and relate the specific formula which can be used to calculate for the cell constant. So in the question, they told us that the resistivity of a 0.02 molar potassium chloride solution is going to be 361 ohm per centimeters, or ohm centimeters. And the conductivity cell having such a solution is being found to have a resistance of 550 ohms. So the question is relating concentration, which is small c, but also it has given us resistivity, which is denoted by ohm centimeters, and it's 361. And after giving us resistivity, we're also given resistance to be 550. So we need to find a statement, or we need to first summarize out our data. So resistivity was given as 361. Resistance, which is denoted by capital R, was given as 550. So you're going to say that from resistance, from the formula of resistance, remember that you said that resistance is the same as resistivity, or constant of resistivity, multiplied by the cell constant, which is the same as length divided by area. So we can summarize it as this. But remember that we have resistivity and we also have resistance. So you just need to make cell constant a subject. And if you make cell constant a subject, you're going to end up with resistance divided by resistivity, which is going to be 550 ohms divided by 361 ohm centimeters. And the value you're going to end up with, if you put everything in the calculator, you're going to end up with 1.5235 per centimeters. So looking at question 2, they have told you to, if at all the same cell was filled with 0.1 molar zinc sulfate solution, had a resistance of 72 ohms, you are supposed to calculate for conductivity of that zinc sulfate solution. Remember, conductivity, we say that it can also be the same as electrolytic conductivity, so they can't be specific. Conductivity is very different from conductance. Conductance, we say that it's a reciprocal resistance, but conductivity can be the same as electrolytic conductivity. So whenever you ask for conductivity, they're also asking for electrolytic conductivity. So summarizing out the data given, they give us 72 ohms as our resistance. And for us to get electrolytic conductivity or conductivity, we get reciprocal resistance multiplied by the cell constant. So reciprocal resistance multiplied by the cell constant, which is the same as length divided by cross-section area of one electrode. We substitute with what we have. We have resistance and we have cell constant, which I have just calculated. So substituting is going to be 1 divided by 72 multiplied by 1.5235. Now I included these units here to show you how the units can be got upon the final answer. So remember that if at all you multiply this ohm is going to go up and it's going to be per ohm. But remember that when you're starting this video, we say that per ohm is the same as Siemens. So Siemens is going to replace that. That's why you're having your SI units of electrolytic conductivity to be Siemens per centimeters, and dividing 1.5235 by 72, you're going to end up with 0.02116, for as long as you put your answer to a minimum of 4 decimal places. Now looking at question 2, you are required to calculate for the cell constant as option 1, and option 2 you are going to calculate for the conductivity of the potassium chloride solution. Now just like we said, you start by summarizing out what the question has presented in front of you. So the question has told you that electrodes are of 2 centimeters squared, and that's area, because we say that area is going to be measured in terms of meters squared or centimeters squared. So area was given us 2 centimeters squared. Now length was given us 1 centimeters. Now resistance was also given as 7.25 ohms. Now they told us it's being filled with a 5% potassium chloride solution, but we don't need the 5% right now. So for us to calculate for cell constant, remember that cell constant is the length divided by the area between the area of one electrode. So length, they told us that they're being separated by a measurement of 1 centimeter, so it's going to be 1. And each electrode had an area, a cross-section area of 2. So for us to get cell constant, it's simply length divided by area. So it's going to be 1 divided by 2, which is going to be the same as 0.5 per centimeters. I hope you can understand how these units have come about. Length is in terms of centimeters, and area which you are dividing it with is in terms of centimeters squared. So if you do the math, this line is going to be per centimeter. I hope you have understood that. So if you go to the next question to calculate for the conductivity, calculating for conductivity is the same as asking you to calculate for electrolytic conductivity. And electrolytic conductivity is the same as reciprocal resistance multiplied by the cell constant, or multiplied by length divided by area. But remember that you have already calculated for our cell constant. So reciprocal resistance multiplied by cell constant is going to give us our electrolytic conductivity. So our resistance was given as 7.25 ohms. So it's going to be 1 divided by 7.25 ohms multiplied by our cell constant, which is the same as 0.5 per centimeters. So this ohm is going to go up, and it's going to be per ohm when you're calculating units. But remember that per ohm is the same as Siemens. So if you get 0.5 divided by 7.25, you're going to end up with 0.06897 Siemens per centimeters. So going to part B, we are going to see that you are being prompted that if the same cell was filled with 0.02 molar potassium chloride solution with a resistivity of 361 ohm centimeters, calculate the resistance. So first of all, you write the formula of what they're telling you to calculate for. So resistance is given by resistivity multiplied by cell constant, which is the same as length divided by area. So since resistance is given by resistivity multiplied by cell constant, and we are given resistivity, but you also had already calculated for cell constant, we just have to make the substitutions. So resistance is going to be equal to 361 multiplied by 0.5. And you're going to end up with 180.5 ohms. Now, since you have understood or you have got the basics of the calculations, let's first go through the other calculations quickly. So in question 3, you are given a resistance of this cell to be 210 ohms. So that's what you summarize out. So resistance is 210 ohms, and you're given specific conductance, which is say that is the same as electrolytic conductivity to be 4.5 exponential negative 3 Siemens per centimeters. You also note it down. So they are prompting you to calculate for the cell constant. So cell constant is the same as length divided by area, but since they give us electrolytic conductivity, we can know that electrolytic conductivity is the same as reciprocal of resistance multiplied by the cell constant, which is the same as length divided by area. So we replace that length divided by area by its original term, and we make what they want, which was the cell constant the subject. So making the cell constant the subject, we are going to end up with cell constant to be equal to electrolytic conductivity multiplied by the resistance. So doing the math, you're going to end up with 4.5 exponential negative 3 multiplied by 210, and you're going to end up with your cell constant to be 0.945 per centimeters as your final answer. Now going to number 4, we are going to say that we are being prompted to calculate for the current that would be flowing through the cell. Now remember that here, looking at the question, you are being given a cross-section area, an area of 4 centimeters squared. So we first note down what you're given. So area was given as 4 centimeters squared, length was given as 2 centimeters. Now if you're having area and you have also summarized out length, that means that at a certain point you're supposed to get cell constant. Now they also give you the conductivity. Conductivity is the same as electrolytic conductivity as 8 exponential negative 7 Siemens per centimeters. So the formula for that, the formula for electrolytic conductivity, or summarizing its value out, is going to be 8 exponential negative 7. But you're also given a potential difference, which is denoted by capital V, to be equal to 10 volts, if you remember your physics. So here we are going to write down the formula of electrolytic conductivity, which is the same as reciprocal resistance multiplied by cell constant, which is the same as length divided by area. So electrolytic conductivity was given as 8 exponential negative 7. Now resistance, we don't have it, so we are supposed to calculate for it, because for you to get the potential difference in your O-level physics, you are told that to get potential difference, you get current multiplied by resistance. So here we are looking for current, which is being asked by the question. We are given the potential difference, so we are supposed to first find resistance. So we're going to use electrolytic conductivity to find resistance. So we do the math, we make R the subject in this formula. You're going to end up with 2 divided by 4 multiplied by 8 exponential negative 7. And you're going to end up with 625,000 ohms as your resistance. So you come and write the formula for finding potential difference. The potential difference is got from current multiplied by resistance. And if you try to make current the subject, which is the prompt required by the question, you're going to end up with potential difference divided by the resistance we got. So it's going to be 10 divided by 625,000, and you're going to end up with 1.6 exponential negative 5 amperes. Remember that current is measured in amperes, and that was the answer which was required by the question. Now the following 2 questions are going to be your self-assessment questions. So you pause the video and you try to logically think about how the answers came about, or how the following calculations came about. In other words, for you to master the craft even more, you can just write down the question and pause the video, you try it out on your own, and then you refer back to the screen to see whether you got the answer right or you got it wrong. So pause the video and try to self-analyze the work yourself. There are only 2 numbers, but I provided you with the solutions to guide you after you're trying without looking at the screens. So make sure that you pause the video and you give yourself a try or an assessment to test yourself. Now with that, let's look at the factors that are going to be affecting the conductivity of the different electrolyte solutions. Now we have two types of electrolytes. We're having what we call weak electrolytes, and you're also having strong electrolytes, just like we looked at them in ionic chemistry. So we're going to be looking at how these factors affect both weak electrolytes together with the strong electrolytes. And mainly, we have in different factors affecting electrolyte conductivity. We also have different factors affecting molar conductivity. But what's common among the two is going to be temperature. So temperature affects both of them. It's an intersection. So it's one of the factors that should be on your fingertips as you're remembering it, because these ones are always asked whenever we ask for questions under electrochemistry, and you should put a specific note on it to understand that it's going to reflect at any time we present a question under electrochemistry. So starting with the factors, you're going to be looking at the factors, first of all, that are going to be affecting electrolyte conductivity, and they're going to include one, electrolyte conductivity is affected by two factors only. I repeat, electrolyte conductivity is affected by two factors only, and we commonly set this question because majority of the students affect or misinterpret it with the factors affecting molar conductivity. So for electrolyte conductivity, we specifically look at concentration of the solution together with the temperature. They are the only two factors that are going to be affecting electrolyte conductivity. Molar conductivity is going to be affected by four factors, as we are going to be looking at them in details as our next heading. So let's first look at the effects, how the following factors, both concentration together with temperature, affect electrolyte conductivity. So one is going to be concentration. So for concentration, we are going to first look at both strong electrolytes, and we also look at the weak electrolyte, how both of them behave in conductancy of electric current through them, provided either is a strong electrolyte or one is a weak electrolyte. So starting with the strong electrolyte, we are going to say that for strong electrolytes, as concentration is increasing, conductivity also increases up to a maximum point, and then conductivity decreases. And the explanation for this is going to be mainly upon four items, and these four items I bolded them. So one of them is going to be interionic distance. Let's first underline them. Interionic distance. After talking about interionic distance, you talk about how interionic distance is going to affect the interionic or the ionic interferences, and how the ionic interferences are going to affect ionic mobility. And after that, you give a conclusion. So those are the four confluences that you need to be talking about throughout these explanations, and they are going to be examined as a must or as a mandatory upon questions under electrochemistry. So one, when we said that when you're dealing with strong electrolytes, as you increase concentration, also conductivity is going to be increasing, but it increases up to a maximum point, and when we reach that maximum point, conductivity always decreases. Now the explanation for that, I said that the main components are going to be interionic distance, ionic interferences, and how ionic interferences are going to affect ionic mobility. And then later, after giving us the impact of ionic mobility or mobility of the ions present in that electric solution, you talk about the conclusion, whether it's going to increase or decrease electrolyte conductivity. So one, we are going to say, as concentration is increasing, the total number of conducting ions per unit volume of the solution is also going to be increasing. So the increase, so this is going to increase. When you increase in concentration, first of all, we are increasing the number of conducting ions present in the solution per unit volume. And once we do so, this increases the conductivity of the solution. So you're going to say that as concentration is increasing further, as we increase concentration further, the total number of ions present in the solution is going to also be increasing, since the electrolyte is going to be completely ionized at all concentrations. Remember that strong electrolytes in solution, they are fully ionized. So the more you increase the concentration, the more you increase the number of the conducting particles. And the more you increase the number of conducting particles, assuming, let's take an example that's a ball. Say for where the concentration is less, the conducting particles are going to be spacious. So it means that the interionic distance, if you look at the interionic distance when concentration is low, is going to be larger. But the more we increase concentration, these particles are going to be closely packed together. That means that the interionic distance, the distance between one ion, one conducting ion, and another conducting ion, is going to be getting smaller. So that's why we are saying that here, so further increasing the concentration, we are going to be causing a decrease in the interionic distance. And once we reduce interionic distance, ionic interferences are also going to increase. Increase in ionic interferences, we are talking about interferences between positive and negatively charged ions. Remember that we told you under electrostatics in your O-level that opposite charges attract each other. So ionic interferences increase as a result of a decrease in interionic distances. So the more the interionic distance decreases, the more the ionic interference increases. The more the attraction between the opposite charged ions increases. And if the attraction between opposite charged ions increases, that means that the ionic mobility is going to decrease. You need to understand the relationship between these three. First of all, interionic distance decreases, and once interionic distance decreases, ionic interferences increase. When you reduce the distance between the opposite charged ions, the attraction between those ions is going to increase. That's what you talk about by ionic interferences. So ionic interferences increase. Once these ions are attracting each other, that means that they are not going to be mobile. They're not going to be free in solution to easily move. That means that as interionic interferences are increasing, the ionic mobility or the movement of ions in that solution is going to decrease. And once the movement of the conducting ions in a solution decreases, obviously our electric conductivity has also to decrease. So that was an explanation for strong electrolytes. Now let's look at the explanation for weak electrolytes. Now remember that weak electrolytes, these ones are going to be affected by chemical equilibria properties. You remember we talked about chemical equilibria properties, that for weak electrolytes we consider equilibrium. Weak electrolytes partially ionize. So if they partially ionize, amount of products must be equal to the amount of reactants. So any concentration we alter is going to be altering equilibrium and is going to cause shifting of equilibrium. So for weak electrolytes, we are going to first say that for a weak electrolyte, as concentration is increasing, conductivity is going also to be increasing up to a maximum point, and then it decreases. And let's look at the explanation under this. Now the explanation under this is going to be further understood under ionic chemistry. I talked about this in ionic equilibria, but I've told you that here we are dealing with equilibrium reactions. So if I told you are dealing with equilibrium reactions, once you increase concentration of the other, obviously, like here we talked about, as concentration is increasing, the total number of the conducting ions per unit volume of the solution is going to be increasing. And if that happens, this increases the conductivity. However, as concentration increases further, the total number of the unionized molecules, like I told you to refer to ionic equilibria and explanations of pH. I over talked about this in ionic equilibria. So the number of total unionized molecules in this electrolyte are going to be increasing, and once they do so, the degree of dissociation obviously decreases. So once the degree of dissociation decreases, the number of the conducting ions per unit volume of that solution is going to decrease. Remember that for us to increase conductivity, the number of conducting ions in solution have to be high. But for weak electrolytes, the more we increase the concentration of our electric solution, we are increasing the number of unionized molecules instead of the conducting particles. So if at all the number of the unionized molecules in the electrolyte increase, more than the number of the conducting particles, that means that the degree of dissociation is going to decrease. So you are going to have less conducting particles, but more of the unionized molecules. And with that, we are going to have a less conducting ability by the few present conducting particles. And this is going to further decrease the electrolytic conductivity. Now here, let's look at temperature as another factor. Now for temperature under weak electrolytes, we are going to look at it like we looked at it in chemical. We are going to consider it as we looked at it in chemical equilibria. Now chemical equilibria, we looked at weak electrolytes. At temperature, effect of temperature on chemical equilibria, we looked at both exothermic and endothermic properties. So here, under strong electrolytes, we just look at kinetic energy. So for strong electrolytes, we look at kinetic energy. For weak electrolytes, we consider whether the reaction is either exothermic or endothermic, and we explain that in details under chemical equilibria. So you're going to start by saying that for strong electrolytes, conductivity is going to be increasing with temperature, and the reason for that is due to increase of kinetic energy. This should be very clear to most of you because I've already looked at explanation of these properties. So you're going to say that as temperature is increasing, the average kinetic energy of these conducting ions is going to be increasing. And once the average kinetic energy of these conducting ions is increasing, the viscosity of the water molecules together with the conducting molecules is going to decrease. Viscosity is just the ability of the conducting ions to be moving, the ability to be moving freely in our electrolytic solution. So the lower the viscosity, the higher the ionic mobility, and the higher the ionic mobility, the higher the conductivity. But for weak electrolytes, we consider whether the solution is going to be whether the reaction or the electrolyte ionizes exothermically or endothermically. Obviously, for us to increase mobility, for a weak electrolyte that is going to be ionizing exothermically, we need to be decreasing temperature to favor high mobility. However, if you increase temperature and also the electrolyte is ionizing exothermically, that means that the reaction will be reversed. The reaction for ionization is going to be reversed. So we are going to have a lot of unionized molecules as compared to the conducting particles, which is going to decrease electrolyte conductivity. And similarly, or the vice versa applies to endothermically ionizing weak electrolytes. So looking at the weak electrolytes one, you're going to say that increase in temperature for those ones that ionize exothermically, increase in temperature is going to decrease the degree of ionization or dissociation according to Richard's principle. So therefore, the number of the conducting ions per unit volume present in the electrolytic solution is going to decrease. And once that happens, that means that also the conductivity of the electrolyte is going to be decreasing. So the vice versa applies to this for the ones that ionize endothermically. For the ones that ionize endothermically, the moment you decrease temperature, you are going to be lowering conductivity. But if you increase temperature, you're going to be increasing the degree of dissociation of such weak electrolytes. And if you increase the degree of dissociation of such electrolytes, according to Richard's principle, you're going to be increasing the number of conducting particles present within that solution, hence increasing the electrolytic conductivity, as we talked about it in details under these statements. Now let's proceed by looking at the factors that are going to be affecting molar conductivity. Now initially I'd say that the factors are 4, but I added on the 5th one, which is going to be viscosity of the solvent. So one is going to be temperature. Like we said, that temperature affects both molar conductivity together with electrolytic conductivity, but the only two factors that affect electrolytic conductivity is going to be concentration together with temperature. But for molar conductivity, we add on other factors such as magnitude of the charge present on the respective ions or the conducting ions that are present in an electrolytic solution, together with the ionic radius of the conducting ions. We also look at the viscosity that is present within the electrolytic solution or the solvent that dissolved our electrolyte. Now let's start with the temperature of the solution. Now just like electric conductivity, the explanation is going to be remaining the same. Still, we are going to explain in terms of strong electrolytes. We also explain in terms of weak electrolytes. So since we have already explained this under electric conductivity, let's just go through it. So for strong electrolytes, molar conductivity is going to increase with increase in temperature, simply because that's due to the increase in the average kinetic energy of the conducting ends. So if at all we increase the average kinetic energy of the conducting ends, viscosity, which is affecting the mobility of these conducting ends, is going to decrease. And once viscosity decreases, ionic mobility is increasing. The moment you increase ionic mobility, that means that molar conductivity obviously has to increase. But for weak electrolytes, we look at whether the ionization is going to be endothermic or exothermic, just like I've recently explained. Now proceeding, we are going to look at the effect of weak electrolytes for those that ionize exothermically and also endothermically, but I say that explanations are going to remain the same, just like that of electrolytic conductivity. So for those that ionize exothermically, their favored mobility is only going to increase. Ionic mobility will increase with increase in the ionization, and for ionization to happen, for those that ionize exothermically, temperature obviously has to be decreased, but if it's increased, there's going to be less ionization, so less of the conducting particles are going to be present in the solution, which is going to further decrease conductivity or molar conductivity. So the explanation is the same as that for electrolytic conductivity. So let's just proceed to the question that is going to involve explanations and the magnitude of the ions together with the ionic radius. So in this question, we told you to distinguish between electrolytic conductivity together with molar conductivity. Now, distinguishing as a defining term or as a major term is simply telling you to state the real definitions between electrolytic conductivity together with molar conductivity. And if we use such a statement, you are going to award quite more marks. That means that you're not supposed to use formulas. You're supposed to use their respective or standard definitions to define such terms. So here you are being given that molar conductivity of ethanoic acid is 0.03 moles per decimeter cubed. Molar conductivity of ethanoic acid of this concentration is going to be 8.5 units at 18 degrees Celsius and 14.7 units at 100 degrees Celsius. So we gave you molar conductivities at different temperatures, and we are telling you to explain the difference in the molar conductivities at the two temperatures. So this one is linked directly to the explanations that are involving for the question. Now, first of all, this is ethanoic acid. If you look at ethanoic acid is a weak acid. But you are seeing that at a lower temperature, molar conductivity was 8.5, and at a higher temperature, molar conductivity was 14.7. So that means that ethanoic acid is ionizing endothermically. Increase in temperature favors more ionization. And the more ionization, the more we increase the number of conducting ions present in the solution. The more the number of conducting ions present in the solution increase, the higher the degree of dissociation, the more we increase the number of conducting ions. The more we increase the number of conducting ions, the greater the mobility. The higher the mobility, the higher the molar conductivity. So you need to explain those questions in that format. And I dare you to go back with your discussion group and you try to discuss that in details. Now let's look at another factor, which is going to be magnitude of the charge which is present on the ends. And this one is going to be simple and direct, as we looked at it in thermochemistry. So here we are going to say that molar conductivity is going to increase with the magnitude. We are saying that magnitude because here there are some ions that are going to have positive 2, negative 3. So the magnitude is saying that irrespective of the sign which is going to be present on this charge. So the molar conductivity is going to be increasing with the magnitude of the ionic charge. So we only consider number. So if our choice is negative 3 or positive 2, we don't care about the sign. We just consider about the number. So the higher the figure, the higher the molar conductivity. And the lower the figure, the lower the molar conductivity. That's the statement by saying that molar conductivity is going to be increasing with increase in the magnitude of the ionic charge. So proceeding, we are going to say that ions which are going to have high charges are going to be more strongly attracted by the oppositely charged electrons, and they are going to be moving faster. That's a simple explanation for that. So the higher the magnitude of the charge present on an ion, the stronger it is attracted to the oppositely charged electron, and therefore the higher the mobility, because it's going to be moving faster. And remember that once the conducting ion is moving faster, that means that also the molar conductivity is going to be high. So another factor is going to be about ionic radius. Now ionic radius, we are going to say that molar conductivity is going to be increasing with increase in ionic radius, because here we look now with ionic radius, we look at this as effect of hydration. Remember that we explained hydration in thermochemistry in details, and we say that ions that have small ionic radius, they are going to be heavily hydrated in solution. And if at all an ion is heavily hydrated in solution, it's going to be heavy, so it's not going to be moving faster in terms of mobility. So its mobility is going to be lower. So if at all its mobility is going to be lower, that means that conductivity or molar conductivity will also be lower. So molar conductivity is going to be increasing with increase in ionic radius, in that the higher the ionic radius of a given ion, the lower the charge density, and the lower the charge density, the less likely is that ion going to be hydrated. So the less hydrated the ion gets, the easier it's going to be, or the more faster it's going to be in solution, as compared to the heavily hydrated ions that are going to be having small ionic radius. So a small takeaway here is that ionic radius, molar conductivity is going to be increasing with increase in ionic radius, because the larger the ionic radius, the less hydrated is going to be the ion, and the less hydrated the ion is, the more lighter it is. The more lighter the ion is, the quicker or the more faster or the higher the mobility it has in the solution, and the higher the mobility, the higher the molar conductivity. But if at all the ion is having a large or small ionic radius, it's going to become heavily hydrated in solution. If you look at most of the transition metal cations, they are always heavily hydrated in solution. So such cations or such ions are going to have a low mobility, because they are heavy in solutions. So if at all they are heavy and they are having a low mobility, it's going to decrease molar conductivity in return. So question about that, you're going to be explaining why magnesium ion has a molar conductivity than the sodium ion. So if you look at what is being compared, we are comparing ions across a period. What happens across the period? What happens to the ionic radius? So you are supposed to explain or discuss this question in terms of ionic radii. So we have also told you to explain why the sulfate ion has a higher molar conductivity than the chloride ion. So here we are considering about light, like magnitude of the charge. The sulfate ion is having, the magnitude is going to be 2. The chloride is going to be 1. So sulfate is having a higher charge as compared to the chloride. So you try to explain that according to the notes that you have taken. And lastly, you're going to explain why the molar conductivity of the lithium ion is going to be smaller than that of the sodium ion. So this is across a group. So lithium ion is going to have the smallest ionic radius, and sodium ion is going to have the largest ionic radius. So you explain how ionic radius is going to affect the molar conductivities of these two in details, and each of the explanations is not going to carry less than 3 marks. So you make sure that you are detailed as possible, and you take for your teacher for verification or for assessment upon what you have done. So let's look at the other last element, which is going to be one of the second last element, which is going to be viscosity of the solvent. So viscosity is simply the ability of the ions to move freely within the solution. So the higher the viscosity, the lower the mobility, and the lower the mobility, the lower the molar conductivity. But if at all viscosity is lower, that means that ionic mobility is going to be higher, and the higher the ionic mobility, the higher the molar conductivity. So here we're simply going to say that the higher the viscosity of a given solvent, the lower the ionic mobility. Hence, the lower the molar conductivity, according to what you have explained. Now looking at the last factor, we are going to look at concentration of any given solution containing the electrolyte. Now we have already talked about concentration under electroconductivity. So here we provided graphs under molar conductivity because these ones are commonly set and you're going to be drawing them in details using the graph papers. So the sketches below are showing the variation of the molar conductivity together with the square root of the concentration for both the strong electrolyte and the weak electrolyte. So you can see the strong electrolyte here, we are having potassium chloride, and the weak electrolyte here we used is going to be ethanoic acid. So this is going to be square root of concentration, and the y-axis is going to be in terms of molar conductivity. So you can see that as you're increasing dilution, the molar conductivity for a strong electrolyte is going to be decreasing, and the same applies to that of the ethanoic acid. And let's look at the explanative details under that. So with that, you can see that explanation of the shapes of the graphs above. We are going to start with a strong electrolyte, which was our potassium chloride, and you're going to see that as concentration is increasing, molar conductivity is going to be decreasing. This is because potassium chloride is going to be a strong electrolyte, and being a strong electrolyte, as concentration is increasing, total number of conducting ends per unit volume is going to be increasing. And remember that we say that as we are increasing the total number of conducting ends per unit volume, we are decreasing interionic distances. And if our interionic distance is decreasing, that means that ionic interferences are going to be increasing. And once ionic interferences increase, ionic mobility decreases, which in turn decreases the molar conductivity. I've already explained that in details. This is just graph work. However, at zero concentration, which we are going to call infinite dilution, and we are going to be looking at this more in details in our next video, where we are going to be looking at Corash's law. So at zero concentration or infinite dilution, molar conductivity is going to reach a maximum value, which is going to be called molar conductivity at infinite dilution, whereby at this point, ionic interference is going to be negligible because the conducting ends are going to be very far apart. So we're going to make a note that molar conductivity at infinite dilution is going to be obtained from the graph by extrapolation, just like you see in your sketch. If at all you happen to sketch that graph, because you're going to do it, especially they're going to be set in paper 2. So if you look at for ethanoic acid, as concentration is increasing, molar conductivity is going to be decreasing. So ethanoic acid is going to be a weak electrolyte, but as concentration is increasing, the degree of dissociation is going to be decreasing. And therefore, since the degree of dissociation is decreasing, the number of conducting ends per unit volume of a solution is going to be decreasing. And the lesser the number of conducting ends per unit volume, the less the ionic mobility present within the solution. And the less the number of conducting ions present within the solution, the lesser or the lower the molar conductivity gets. So you're going to say that instead of concentration, reciprocal of concentration can also be used as a dilution factor. So under this, we are going to be looking at how molar conductivity can be affected with dilution. So the first graph was about concentration. So here we are going to be looking at variation of molar conductivity, how molar conductivity can be varying with dilution, and we are going to be looking at that in details. So we say that we made a note here that note that neither the graphs against concentration nor the against dilution begins from the origin. That means that you can't have zero molar conductivity. So the graphs are just originating. The graphs are going to be coming from the air, or they don't start from the origin. They don't start at zero. We can't have zero molar conductivity. There's always going to be some form of molar conductivity in any given solution. So the graphs do not coincide anywhere too. You have not seen any graph of any electrolyte coinciding with the other. So molar conductivity, you are seeing an extrapolate up here, showing that how you can get molar conductivity at infinite dilution. So let's dive into the content or the explanations under that. So the explanation you're going to have under that, we are going to say that for potassium chloride, as the addition is increasing, the molar conductivity is also going to be increasing to a maximum point at which it's going to remain constant, and this is going to be called the point of maximum or infinite dilution. So potassium chloride is a strong electrolyte. So being a strong electrolyte, as the addition is increasing, its ions are going to be fully ionized in solution. So as the addition increases, interionic distance is going to be increasing. And once interionic distance is increasing, ionic interferences are going to be decreasing. So once ionic interferences decrease, ionic mobility increases. So at zero concentration or at infinite dilution, the ionic interference is going to be simply negligible. And we are going to make a note for that, and we say that for molar conductivity at infinite dilution is going to be obtained from the graph simply by extrapolation. Just like you saw, I made an extrapolate and I denoted that as infinite dilution at infinite dilution. So I denoted by an inverted V together with a subscript of O at the end. So for ethanoic acid, which is our weak acid, as dilution is increasing, molar conductivity is also increasing. So ethanoic acid being a weak electrolyte, as dilution is increasing, degree of dissociation also increases, and therefore the number of conducting ions per unit volume of the solution are also going to increase, which in turn increases the molar conductivity. So now this brings us to the end of this video, and you advise subscribe to the channel, share the video to your friends, and subscribe to the channel so that we can all benefit as a group and you don't miss out at any coming videos. So we meet in the next video where we are going to be looking at factors or Corash's law of independent assortment under conduction or under molar conductivity. We look at calculations that are going to be involving molar conductivities at infinite dilutions and how we can apply them under ionic equilibria. So see you in the next video.